mate. Share. I need that talking stopped. Stop share. Share screen. Image mate. Share. And admit Mr. Jackson. And admit Miss Megan. So, can you name some things that collide?
Avalanche.
What does the avalanche collide into?
Wind. Wait. Wind and cold and sweet. Ice.
I need things that where one thing collides into another.
Wind and energy.
Guys, think about what we've done over the past 2 days. Where one thing collides into another.
Transferability.
Come on, guys. Anybody play sports?
Yes.
Okay. Tell me something where one thing collides into another. Allie.
A baseball bat and a ball.
Baseball bat and a ball. Tell me something else where one thing collides into another. Hunter.
A football.
A football into what? A person, like their hands, right? Or their foot if they're kicking it. Yes? Okay. Something else where one thing collides into another. Michaela.
Basketball and the ground when you dribble it.
Basketball on the ground. Okay. Think about what we've done in my classroom where one thing collides into another. Logan.
Cars.
Car into
Car.
another car, right? Okay. What about a soccer ball?
Yeah, that's what I was fixing to say.
Foot and a soccer ball. Okay, so we understand what the word collide means, right? Collide is another word for crash or to impact. Impact being the verb, meaning hit. We understand that, yes? Okay. So lesson 7, we were supposed to end with something, but we ran out of time. I'm going to go through and grade some of my students' work from yesterday, those that I didn't get to yesterday, at the same time that I'm grading today's work, okay? But we didn't get to finish out yesterday's lesson. So let me set up the end of yesterday's lesson. Sorry for desk are not trash holes. We're not going for knock out this or knock out the teacher. There's a pencil on the floor. In case we get the, if you don't want it, go put it over there. Okay. Innocente. Ugh. Allie. Ugh. Okay, you can put it over. Oh, I gotta have your test back. Take out your test right there. Do that test paper and go put it over there on top of that orange and blue box. Yeah, no, orange and blue. Great. Alex, keep walking. Alex. Allie. Walking. Right there, perfect, thank you. Okay, now you gotta back up. Keep going. There you go, right there. There you go, just keep it aside a little bit, because I like to have everything. All right, I know the desk isn't really wide. You remember how we set this up? Ricardo, you guys move back.
Ricardo walk.
Allie's gonna walk. Innocente's gonna run. And both of you are gonna go into the desk. So Innocente is literally gonna run into the desk.
I'm gonna run into a video.
Remember, it's supposed to be into me. That's no go.
It's gonna hurt.
This will keep it from rolling because I have to speak not to roll. I've learned. Okay. The idea is not to transfer a whole bunch of energy up me because I'm not supposed to lift anything above 20 pounds. This weighs 150 pounds, and I had to lift it yesterday over the doorways. Yeah, I had to lift it over 3 doorways. That wasn't real good. My neurosurgeon was pretty big all that. Okay, the guy that did this. All right, so Allie, you're gonna be walking, and you do not stop before you hit the desk. You have to put your force, your energy into the desk, just like the continuum walk. Like pretend you're blind and you just walk into it. Innocent, I know the temptation is to stop before you get there. Don't. Just pretend like you're blind and you run into it. Literally, run into it.
Okay, so Allie just
It is the most bizarre thing, I know, because the desire is to stop, right?
Yeah.
This is the one time y'all get to actually run into the desk, not me, the desk. I'm not the linebacker here. You're not nailing me. That's the linebacker. You're nailing the desk. Okay?
Pretend the desk has a football and you want to tackle it.
Yeah, you want to tackle that, but don't break it. Okay? Allie, you're walking. Hey, you're running. Go.
Oh.
Okay, move out the way. Come in. All right. So, who hit the desk with more force? Innocent. Who brought more energy to the desk? I know my foot was holding it, but did anybody notice that it still moved when he hit it?
Yeah.
Did anybody notice it moved any when Allie did it?
Yes.
It did move?
Yeah.
I didn't notice it move at all. I did notice that my knee got pushed back a little bit. That's enough. Because I think the nut who came up with that design, remember, it's supposed to be running in the future. It's good. Run into the teacher. Yeah, right. Because when I told Mr. Williams, he's like, "You're supposed to pretend." I said, with children pretending, no, you kind of have to act it out. So, no. But you guys get the idea that you transfer energy. In a sense, I transferred his energy into the desk, right? You didn't bruise your hips, did you? Okay. And Allie, you didn't bruise yourself, did you? I asked because I've got a bruise right here from where I ran into a desk last week. Big old bruise. But then again, you guys see I move around the room fast, don't I? I do it all the time. And I'm a klutz. Okay. Okay. So is there a sound, or was there a sound when Innocente ran into the desk?
Yes.
Yes. Even with my foot holding it in place, there's still a sound, right?
Yeah.
It dragged. So some of his energy transferred into sound, right? Because he was carrying a lot of energy from running. Yes. And we already said before that sound is energy, right? So some of his energy of movement transferred to sound energy. Does that make sense? Please don't. Please don't, because he's going to say it's from Miss Vandermeer. No, it's not. I don't know what's wrong with the child. Maybe he hit his head last night. I don't know what's wrong with him. Okay. Sometimes a moving object stops after a crash. What happened to that object's energy?
It went to the other car.
It went to the other thing, right? Yeah. Remember us discussing that wreck that Adrian saw?
Yeah.
So bad. The concrete stopped the car, right?
Yeah.
What happened to that car's energy?
It
transferred to the concrete.
That's like a pool table. And when it transfers, if a ball is another ball, it transfers the energy against the other one.
Do you think there was sound when that car hit concrete?
Yes.
Yes. Do you think there was heat when that car hit the concrete?
Yeah.
So some of that energy transferred into sound energy, and some of that energy transferred into heat energy. Okay, make sense?
That's what's going to happen.
Yeah, no, let's don't run into a tree. Okay. So if in a sente, if something had gone wrong and he decided to do his own thing, and instead of running into the desk, he ran into Allie, who was walking. That would have hurt Allie. Who do you think would have been hurt more, Allie or Innocente? Allie, because who was bringing more energy? Innocente. Allie was bringing less energy because she was moving how? Slower. And what did we say about energy and speed?
They're alike and different. What? They're alike. We said that.
There's more energy where there is more speed. So the fact that Allie was moving slower meant that she was bringing less energy. Innocente was moving faster, so he was bringing more energy. And the way energy works, and the way heat works too, you go from more energy to less energy. So Allie's energy is not going to transfer to Innocente. Innocente's energy would transfer to Allie.
How dare you, Innocente?
Okay, but does that make sense, guys? Does that make sense?
Yeah.
Okay. All right, going on to today's lesson. That was finishing out yesterday. Okay, so our investigation question right here is what's in pink on the board. Does an object's speed, I'm going to zoom in a little bit. See, even though that's a crazy lab, it brings a lot of concepts together that you might not get without that weird lab. No students tend to not forget running into a desk. I guarantee that neither one of the other teachers would have you do that.
That's why we're never gonna forget it.
No,
That's why at recess there's that brown sugar that we were crushing.
no.
Actually, we are going to the first one, and there's no sugar.
And we're not going to get the teacher in trouble by doing that. Otherwise, we won't go outside. No, we're not. We're not crash test dummies. Does an object's speed affect energy during a collision? Collision, two things hitting each other. We already talked about it. Remember soccer ball and foot, football and hand, football and foot, collision. Everything is an object. A person could be an object if we're studying it. I don't want to be the object. Understand that object just means the thing that's being studied. Okay, that can be a human. I'm the object every 2 weeks. I was the one getting the needles, and I was the one that had 2 doctors in there studying me. Because I'm the only one that has it like that. She said I'm the only patient that gets that treatment. Kind of expensive. I'm the goofball.
So you're worth like 10 million?
Oh, I've had so much work done on me. I've had 5 or 6 surgeries. I had a transplant. I've had a transplant, but I won't say of what. It's hilarious. You wouldn't believe me. Okay. No, someone else put it in. Yeah, someone else put it in. Yeah, for real. And it didn't make me better. I rejected it. Told you, I'm the weirdo. Yep.
I just had tears.
See this? This thing I had 6 times.
That.
All right, back to our investigation of transference of energy. Got it? So when we talk about an object, we're just talking about the thing we're studying. That could be what we looked at yesterday was a ball, right? A few moments ago, we were looking at 2 people crashing into a desk. The thing you're studying, the object could be a human. It's just the thing you're studying. Okay. All right. How can we vary, in other words, how can we change the ball bearing speed? And he asked a question, what is a ball bearing? I'm going to show him what a ball bearing is because apparently he forgot from yesterday. These things. Those.
They look so heavy. They look like magnets.
Yeah, no, they're not magnetic.
They look like. Can I hold one?
No. How can we vary? We're going to run out of time, guys. How can we vary the speed of one of these things?
By looking at it.
No. What? We could push it.
But that would be.
That would be an unfair investigation.
We could time it.
That doesn't vary its
We
speed.
could make them drop higher.
We could make the ramp higher. So we could put 2 boxes up there instead of 1, right?
Yeah.
What else can we do? We could what?
Make the roller longer. Get a longer roller. We could use a meter stick.
Well, if it had a groove in it. Because if it didn't have a groove, it'd be falling off the edges all over the place.
Wait, meter stick doesn't have a groove?
No, it's totally flat.
I thought it did.
Totally flat. Okay, so this time we're adding something to the mix. Right behind you, there's a box that has ingredients. It's a silver box. Spin the other way, Bryson. In the silver box, there's a clear little, it looks like it's glass. Hand me that.
Baking soda, vinegar.
Logan, hush, please. Do you see the little clear? Nope. In the silver box. Within the silver box. Silver box up on top. Yeah, Bryson. See the silver boxes that are stacked up on top of that big clear thing? Yep. There you go. I need one of those clear things in there. Yep, that. Yep, I just need one. Bring me that. So this time, instead of letting the ball just roll down the ramp,
I get it.
we're gonna have it roll into this. And we're gonna measure how far this goes. Okay?
Can I try that? Sure.
Okay. But we're gonna watch because it's gonna be on this floor, it's gonna push this, whereas on this paper and on this, it's not gonna make this scoot because this has friction on it. Okay, this is called a catch. Okay, so if we threw this into the catch, first of all, I'd break this. Okay, because it's plastic. But if we threw it into the catch, would that affect the speed?
Yeah.
It would.
Slow it down. No, it wouldn't. It would make it go faster.
It would make it go faster.
Because if you push it, it will go faster.
It would make it go faster, but it would also break this.
Yeah.
Okay, so we can't throw it in there. We're gonna set up the design just like we set up yesterday with the tape to measure it and let it roll down naturally. Everybody understands this, how we can set it up so it's a fair test, right? What is it? From hitting the desk?
I don't have any.
Okay, so here, here is the procedures. Here are the procedure steps. So look in your notebook. Is there anywhere for you to write down the procedure?
No. Yes. No, there's not.
No. So if you guys would look up here, we're gonna read through it quickly and you're not gonna write it. But you're gonna have to, number 1, be quiet. Number 2, pay attention. And we're gonna have to make a graph, which for my students last year, that was very confusing for them. So yes, so you're gonna have to stop talking and pay attention.
What's a graph?
No, we didn't make a graph yesterday. We made a chart yesterday. All right, so starting with conductive investigation on a flat surface. So our floor is relatively flat. Choose a textbook at least an inch thick. We have a box that's 3 inches thick. Flat on the surface, we've created a ramp. That's already done. The ruler's 28 centimeter mark is lined up with the edge of the book. Already done. Piece of tape on the work surface so the edge lines up with the end of the ruler. That's the start line. Already done. Place the ball bearing catch against the end of the ruler so that the front open edge, open side, lines up with the start line. Easily done. Okay, so this gets lined up just like that. Okay, and this might take several tries because it might knock the catch off. It has to go right into the catch. And then we'll release the ball bearing from the ruler's 7 centimeter mark. Measure how far the front of the catch slides from the start line. So this time we're going to have to use this because we'll be measuring how far this slides away from this ruler. Okay, so it's a little different procedure. We're not worried about the meter mark, not today. Okay, I'll leave that on the floor. All right, so we do this from the 7 centimeter mark, and we measure how far this slides away from the end of this ruler. Make sense? All right, we do this 3 more times for a total of 4 times. Then we go to the 14 centimeter, the 21 centimeter, and 28 centimeter. I started to make the graph yesterday after school. 5th grade teachers found an issue with the Chromebooks yesterday, so my youngest son, who uses the Chromebook past 2 years, came up with my husband, and Colby was trying to help this board and Chromebook try to figure out the solution. Couldn't. The district ordered clean and there's not a single person on the district's payroll that will work on these things. Isn't that so smart? Great. So when y'all get to math class, you guys might have an issue with the camera. We don't know how we're going to address this. 5th grade's definitely going to have an issue with it. In my class, we're not really using the phone yet. AR. Not going to affect my class yet. Probably not going to affect Daniel's class yet, but it might affect that. Not a big deal. But I finished setting up. Okay. So you can set up your chart at the same time I set up my chart on the board. All right. You guys don't need to do this. I'm doing this because I'm having to use this chart for 3 different classes. No, again, you only need to put yours in the chart. Okay, so obviously, since I've already marked these off in blue, your class will be dark blue like it was yesterday. Okay, use the same colors I used yesterday. You'll be dark blue, second block will be bright green, third block will be pink. Okay, so I'm gonna have the same person do the timing as yesterday. That was consistent. Carter, have you done any mining this week? Hey, have you? Hey, has? No. Okay, so to begin with, all we're looking at, speed has to do with the angle. You want to help her measure that way? I have 2 people measuring. Yes, so I'll let her measure and then let you measure and if there's discrepancy go to the middle number. Okay? All right, so we're at 7. And right here, that's 0. We're going to see what it needs to be. So it moves from here. We want it to be very All right, I need you guys not move it. You need to look at it. Front of the catch. Where's the front of the catch? What is it? We do 4 trials total. 7. We got 7. Okay. 4.3.
4.2. Four and a half.
4.5.
Okay.
Okay, now move it up to 14 centimeters. Do that one again. So it's a wobbly on it. Okay, this time you're going to go from 21.
Eight point two. Nine. 9.1. 9.2.
Oh, I got to do the average of these. Now you go 28. You go all the way to the top, pretty much where that tape is. And now it wants to roll the side. It's so hard. Guys, I need you to be real quiet, not bumping desks, okay? Because this is where it's hard to keep it on the ramp. It's really hard to make a good kit. And then stop bumping desks, guys.
Nine. 12.8. Whoa. Eleven.
That's all of them. All right, put the, actually hand me the ball. So I'll do the average.
What is the bar? Wait, what was the last one?
Last one's 11.0 and the average is 10.7. Good job. Okay, so we didn't talk about this yesterday, but we need to talk about this today. Why do you think we don't run 1 or 2 trials on each measurement?
Because they need more investigations to see.
Well, look at number 28 centimeters. We had one where the data was 9.0 centimeters. That's how much it moved it. We had another one where the data showed 12.8 centimeters of movement. Right? That's a big range, isn't it?
Yeah.
When we averaged it out, it came out to be 10.7 centimeters. It
So, like,
looked like, well, you get more accuracy when you have more data points to average. When doctors are trying to study efficacy of medicines or efficacy of a surgery, they don't study 1 or 2 patients because you could have anomalies. You could have one patient had some weird thing go wrong. Like I'm generally the weird one. Something might work really well for me and not work well for 99 other people. Like I said, out of Dr. Harris's 1,000 patients, I'm the only one that has these treatments because I'm the only one that doesn't respond to all these other normal treatments. Yeah. I'm also the only one she's ever sent to Baylor. If someone's come in. Maybe my door is always unlocked. Come in. Have you already had your stent taken? Okay, come sit. Here we go. Okay, you need to turn to page 23. You need to copy that question at the top quickly. Come on, get it going. Okay, because you've missed an hour of class. It's 9:05. Have fun. Okay, so with studies, you have to have multiple trials in order to get an average and to get accuracy. Does that make more sense? Even at Baylor, and where I went to Baylor is called the Headache Clinic. Okay, they have patients that come all the way from Chicago, Illinois. They have patients that come from South Louisiana. They have patients that come from Arizona. They're used to dealing with patients that come from all over the country because they are the top. There's like 2 places in the US that take the hardest to treat patients. I'm one of them. Yeah, I'm that person. Okay. I was still the only patient getting those treatments. So I would not go into a trial like that because I would be the one that would stand out. Got it?
You would be the only one.
Yeah, I would not fit into a trial like that. They wouldn't want me for one of those trials. Now, that other thing that I told you about, I would go into that trial because that's a more common thing. Believe it or not, pretty common. Transplant. But I failed it. Most people succeed with it. I failed it. Very people transplant. And then I got rid of it a few minutes later.
This energy? No,
no. It's a very expensive transplant.
It's not expensive.
About $15,000.
You're telling me to do that?
Yeah, they put you to sleep to do it. It's gross.
At least it's not permanently.
Yeah, it affects you permanently because you get that person's bacteria.
Yeah, you don't know what it is.
It's
like,
I got put to sleep for it, thankfully.
Yeah.
The doctor said, I wish I could have been put to sleep for it. The doctor has the worst end of things, literally. He's like, I wish I could have been put to sleep. I'm like, yeah, sorry about that. He's definitely got it worse, not me.
Energy transfer.
And some people have to take them as skills. I'm like, yeah, please don't tell me I have to do that. No,
Take them as skills. That's energy transfer.
that's a whole nother level of.
What's the worst part? You say
That's the worst thing imaginable. What?
And this energy transfer, it'd be stuck inside you.
Yeah, it's stuck in a capsule, but still just a part of it. Can you imagine throwing that up?
It's pretty hard.
Okay, so that's a chart. But you know how the saying, a picture's worth 1,000 words?
No. Never heard of it. What? Yes. What? Never heard of that.
You can write all the words you want to in a card for Deasia and it'll make her feel better. But the pictures you guys drew her, especially Logan's, that is what she's gonna love hanging on her walls. Pictures are worth a lot. Words are sweet, guys. They are. But pictures are worth a lot. Y'all understand what I'm saying?
Yeah.
The picture of Colby back there holding the puppy. Okay, that's Colby a couple years ago. It's sweet, right? That just, oh, especially girls who see it, they're like, oh, cute puppy.
Yeah.
Colby could have wrote a sweet poem and it wouldn't look nearly as sweet. Especially when you look at it, you glance at it, you see it for 1 second.
Puppy.
That poem versus the picture. The picture's worth a lot more, right?
Yeah.
Same thing with data. Colby was 12 in the picture. Same thing with data. We can look at that table. We see that when we move the ball farther up the ramp, the ball made the catch move farther away. We can see that with the numbers, right? But if we could somehow transfer that to a picture, it would probably be easier to see and understand, right?
Probably would be.
That's why we're going to change that into a graph. Make sense?
Yeah. Is this energy transfer?
Yes, that's energy transfer. You transfer it to a catch. Okay, so we have a graph back here.
I only have one stage.
At the top, distance catch traveled at release points, because that's what the 7, 14, 21, and 28 centimeter marks are. Those were the release points. That was the places that Kaylee was releasing the ball from, were they not? So you need to label this. Bryson, turn your page and start labeling. Distance catch traveled at release points. And we're going to have to change up our numbers on the side because our catch moved more than 7 centimeters. Our catch moved, in one case, 13 centimeters.
Yeah.
We're going to talk about that in just a minute. And we're actually going to plot the averages. We're not going to plot each one of the trials. We're going to plot the averages. So our averages range from 4 to about 11. So our highest one is going to be this will be 11. This will be 0. So 1, 3, 5, 7, 9, 11 is too much. 1, 3, 5, 7. That's too little. 2. Please stop playing with that. 10. This will be an approximation. So 2, 4, 6, 8, 3, 5, 7, Okay, so the first thing I need you to write here is distance, catch, traveled, centimeters. Write that, please, because we have to label our two axes. I need you to label y-axis right here. Have you made bar graphs like this in math yet?
No.
Okay. You're expected to make these for science class. Like I said, science is more advanced than math or ELA. Zero, then 2. I know we skip a little bit there. Oh well. 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, we're going to put the 11 right up here. Okay. And that's going to put our 1 somewhere in here. Okay. Y'all see how I did that? Make sure you labeled y-axis. You see it up here? And then down here, 7 centimeter, 14 centimeter, 21 centimeter, 28 centimeter, and label x-axis. Okay. X-axis goes this way. In every single graph that you ever will draw, forever, college, after college, always, x-axis goes this way. Y-axis goes this way. Let me show you a way to remember this. I've had to show this to my husband because he forgets. Seriously, watch. Y is written like that, isn't it? You see this? That's how you can remember it. The Y is written that way, just in the form of the letter itself. The Y is written it forms part of the graph. Got it? So you need to have that 11, 10, 9, 8, 7, 6, 5, 4, 3, 2. The 1 is in between, the 0 is down here. You need to have all that labeled. And then 7, 14, 21, 28. This distance catch traveled in centimeters. These down here need to be labeled centimeters. Down here is ramp release points.
Something wrong.
What?
Why without words we're doing something wrong.
Correct. You need to label all of this. It's a lot to label.
Why makes no sense.
Then you weren't paying attention.
I paid attention, but it didn't make sense.
Okay, so the average is 7 centimeter release point is 4.2. So that's about 4 centimeters. So put a line here, here, here. Look on the graph. I mean, look on your chart.
We're just making a bar graph.
Yes. And the average column says the ball bearing catch traveled 4 centimeters.
4 centimeters.
You see it on your chart? So you go to the 4 and you color it in.
Barely colored.
I'm barely coloring mine because I have to keep erasing this and hopefully I won't rip it. Okay.
I got you to get 3 books.
Because I don't have 3 books.
No.
Logan, enough. I erased it from last year. My data was different last year. All right, 14 centimeters. How tall should that one be?
Should be 11.
No, look at the average centimeters traveled for 14 centimeter release point. 6. So 6. And again, I'm doing mine real light because I have to erase. Guys, you can make yours look a lot neater because you don't have to erase yours 3 times during the day and then again next year.
Wait. You didn't use this through the whole year?
I use it again next year.
Oh, wow.
This is last year's notebook.
And then you buy a new one?
I can't buy them. These are what's given to me. And I don't have extras. So this is last year's. Okay, so you can barely see mine. It looks like a shadow, but it's there. Okay, at 21 centimeter, how tall should that one be? 9. So that's up here. This is a bar graph. Again, I have to erase mine between each class. Each class will have different data. Yours needs to be darker. You don't have to erase yours every class. And you don't have to reuse your notebook next year. I do. Don't you dare scribble. Okay. And then your last data point. Boy, you can really tell mine. You can do your own, right, on your last one?
Yeah.
Okay. So 10.7, if we round that, that's going to round up to what? 11. Okay. So do your last one on your own. Now, while I'm thinking about it, I'm going to go ahead and erase this. That way, I already have a clean graph for my next class. Okay, couple questions. How did the increasingly higher release points relate to energy? Because it's 7 centimeters away from the end of the ruler, that was a lower release point, right?
Yes.
When we went up to 28 centimeters away from the end of the ruler, that was farther away, right?
If it's high, if the angle's higher, it goes down faster, so it gets more movement, so it can go farther.
Right. So did that mean that a larger number of centimeters away from the end gave it more energy?
Yes.
Good. So the higher the release point, the more energy we gave the ball bearing, right?
Yes.
Okay. So we know that putting in more energy causes the ball bearing to move how? Faster. So ramp release points, the higher that centimeter rating right here, the more energy we gave it, right? So let's label that. More energy input, more speed, and then an arrow this way. That way we know that as we got higher on these numbers, we're going away from the end of the ruler, we were adding more energy and we were adding speed to it. Does that make sense?
So when it has a longer angle and it's taller, it gets more speed.
Yes.
Oh, that makes so much sense.
Kind of like if you're swinging a golf club at a golf ball, if you pick up that golf club
Do it higher.
farther, you're going to add more energy and make it go farther.
Oh, yeah, I get it now.
Yes, ma'am. Bathroom. We got one more thing to add. Do you want to wait till we add it or do you want to go right now?
I'll wait till we add.
Okay. Okay. How do you think the distance a catch travels relates to energy? Did the catch have any energy before it started traveling?
No.
No, it was just sitting still, right? So,
But when you dropped it did have energy.
So when you drop the ball, where did the catch get the energy?
The ball. Your hands. The movement.
The ball gave the catch energy, right?
Yeah.
So the ball transferred its energy. Yes?
From speed and movement.
Okay, so it took more energy to push the catch further, right? So
the catch was
more energy output. As the distance the catch traveled increased, more energy output. Does that make sense?
Yeah.
Because as the catch moved more, that meant more energy was being pushed out. Everybody understand that? Okay. So we're going to label that also, okay, with the arrow.
I just erased that.
Sorry.
Because I saw it before and then I erased it.
I wanted to explain it first before we labeled it. Okay, it's my third time to notice you with the water bottle. Put it down. It's not supposed to be in the vicinity of the computer. You've already been told that. Sit down and get your work done, Hunter.
So if you keep on doing it over and over, the catch just keeps on getting more energy?
If you had a longer ruler and you release the ball from a higher angle, it would give more energy to it.
But the catch does get energy from the ball.
It does. It does.
So anything can get energy?
You can transfer energy to anything.
Anything.
Yep.
So you're telling me you can transfer energy to water?
Water's energy is in the form of motion.
Oh, yes, you can.
I wish I could transfer energy from her to me, because she's got lots of it. Lots and lots of energy.
And you got Is she the one who did this to you?
No, that's my surgery.
Oh,
I had major surgery.
She has scratched it.
Oh yeah, she scratched it before.
It hurts.
Yeah.
Wow.
See? That's her favorite person in the world right there. Oh yeah, that's her pop.
Because he's always funny.
He lets her do just about anything she wants.
So that's, yeah.
That's her pop. Okay, the ball bearing with the most energy pushes the catch the furthest, and the catch with the most energy travels furthest. If we had a meter stick with a groove down the middle, we could really push that catch out a long way, right? Because we could have 100 centimeter run up to the catch, and we could really make that catch run out a long way.
Leaning on the table. Leaning on the table.
The catch and ball bearing can be thought of as a system because they are two objects that interact, and the distance traveled is one indicator of energy in that system. Make sense?
Uh-huh.
So when it was Allie and Innocente with the desk, right?
Uh-huh. Yeah.
So Allie and that desk were a system. She brought her energy, her chemical energy, to the desk, right? She transferred her energy to the desk. And Innocente and the desk were a system. He brought his energy to the desk
So the desk had,
and transferred it,
so the
right?
desk had twice as much as energy.
No, it had some more. Okay? The distance traveled of that desk was an indicator of energy in that system, except that somebody was trying to hold the desk in place somewhat, so the desk didn't roll over. That would have been very loud. Go, Logan. All right.
This lesson wasn't long.
Does the ball bearing have more energy when it moves quickly or slowly? Does the ball bearing have more energy when it moves quickly or slowly?
It has more energy when it goes faster.
When it goes quickly.
When it goes quickly, it goes farther.
Did all of the ball's energy get transferred in the form of movement?
No. Yeah. Not all of it. It still had some problem. Wow. Because when Innocente hit the desk, he still had some energy.
He did. But was there anything else, any other kind of energy transfer that happened other than movement? Sound. So some of that ball's energy transferred to sound energy.
So that's why when you hit something, it makes no. Wait.
Energy transfer also goes to sound. Please sit down and stop playing with the pencils. Guys, I love mechanical pencils. But when you're taking them apart, that means it's becoming a distraction and it becomes mine. Got it?
Mm-hmm.
Colby loves it when he gets mom's tools that way. Are you understanding me? And Mila loves to try to swipe them from me. All right, stop playing with pencils.
And
All right, so when Allie and Innocente ran into the desk, it made sound, right?
Yeah.
So some of their energy transferred to sound and some of it transferred to movement. Okay, makes sense?
Yeah.
Some of that ball's energy transferred to movement of the catch. Some of it transferred to sound energy. When the car tried to hit that gas pump unsuccessfully, it made sound, a lot of it. It made heat, and its movement got stopped by the concrete. So all that car's energy went to various forms. Does that make sense? Yes, no, anybody here?
Yes.
Okay. The fastest ball bearing, does it have the most energy or the least energy?
The most.
The most energy. And we know that because it moved the ball, the catch, what?
Farthest.
The farthest. The process by which energy moves from one part to other parts of a system is called energy transfer. Makes sense, right? We've talked about transferring energy before. Our next lesson, tomorrow's lesson, is going to be talking about what happens to energy when objects collide.
Ooh, yeah. That's easy.
Yeah.
Oh my.
Tomorrow, you're going to be drawing pictures and writing what we did today.
Energy transfer? That does not sound
Today we did the numbers and the graphs. Tomorrow you're going to be drawing it,
Ooh.
and then you're going to have a conceptual checkpoint that deals with the golf club and a ball.
That's easy.
No, it's not.
Do you want me to get a golf club?
No.
The golf club sounds hard, but the other sounds
Tomorrow's conceptual checkpoint is one of the hardest ones of the year. Uh-huh.
How do you even tell us that? I'm scared.
It's going to ask you about collisions between a golf ball and a golf club. You're going to have to draw it before the collision, during the collision, after the collision. You're going to have to tell me about all the different energy transfers, not just about it hitting. But remember, energy transfers aren't just about movement, are they?
No.
They also generally involve what?
Hearing.
Hearing,
Sound.
sound.
Feel.
So when a golf club meets a golf ball, what is there?
Sound.
Sound,
Movement.
as well as movement. You're going to have to draw pictures before they hit, when they're hitting, which is during the collision, and after the collision. And you're going to have to tell me what happens to that ball through all three parts. No, it's pretty darn hard.
No, not that hard. Whoa, kidding. You sure about that?
And again, we don't do well on these. This shows Mr. Williams that the experiments are a waste of time. I've talked to the 3rd grade and the 5th grade science teachers. They're not doing experiments. And their kids are doing better on their tests. So if my kids don't do well on the test, guess what Mr. Williams is going to say? We don't need to do the experiments. We don't need to do the experiments anymore. Is that really the lesson we want to give them?
No.
So what do we need to make sure we're doing?
Do good on the test.
Do well on the test so we can keep on doing experiments. Do I make myself clear? Okay. I need to go around and grade everybody's work. This is yesterday's and today's. Let me get this done first, please. Stop talking. Logan, let's grade yours first. No, let's get this stuff graded first. No, after I graded it. Stop talking, please, so I can get all this done, okay? Guys, my son. Guys, you want another 5 minutes off recess? Hush. Oh, you're not. I have 3 minutes to go.
What really?
I don't know that. Okay, well, we only have 3 minutes to go. Jordan, hold your hand. How much everybody? I think everybody. Guys, quiet, quiet. Y'all get what quiet means.
Oh,
I don't think everybody does. Okay, when we come back, I've got to grade Aaliyah's work from today, and I have to grade Ricardo's work from today and yesterday. Like everybody else is graded. All right, guys, line up. Close up your Chromebooks. Close them up. All right, lined up. Last person out, shut the door. Got it? Okay. Now you're going to take the thing out. Please don't tear up the sand. Let's go.
Ah.